Então eu quero chamar para a evolução do projeto de sprinklers, Wes Baker. Wes Baker é especialista técnico de engenharia na divisão de Engineering Standards da FM Global. É responsável por datasheets, diretrizes de instalação para sprinklers usadas em proteção de armazéns. Wes Baker é membro da Society of Fire Protection Engineers e da National Fire Protection Association.
Thank you, everybody. Thank you for having me here. Today's topic is basically going to be a history on fire protection as it originates in North America. So when we look at what we had back in the early 1990s, the first thing that we came across from a design standpoint was pipe schedule. And hopefully many of you are familiar with that, and it's based on the sizing of the pipe, whether the occupancy hazard was listed as either light hazard, ordinary, or extra hazard. And that worked quite well throughout the early 1900s. But about the 1940s, 1950s, we started to see quite a bit of changes taking place in industry. The first of which was a lot of facilities that were previously made out of either wood or reinforced concrete were now being built with steel. Steel's great. The only problem with steel from a fire protection standpoint is that it doesn't take much heat to lose the integrity of the steel. So there was always that concern now about collapse of buildings. In addition to a change of steel, we started to see much higher storage. Along came the forklift truck. So before the 1940s, 1950s, storage was basically as high as you or I could physically place it, which for me that's not very high. With the forklift truck, storage could go much higher, and with higher storage comes higher heat release rates. In addition, we started to see a change in the type of products that were being stored in warehouses as well. We used to have a lot of products that were either made out of paper or non-combustible, but that changed quite a bit in the 1940s and 1950s when plastics were introduced. So when you put all of those changes together with pipe schedule systems and warehouses, we started to see quite a bit of results that didn't go our way. So we realized we needed to make improvements. So one of the things that came out in the 1950s was a concept, was a new type of sprinkler that was introduced. It was the standard spray sprinkler, the K80, for those who are familiar with it. In fact, if you look above you, you might see that this particular sprinkler is installed as well. In addition, we also had a new concept that came out, and this was density. That's a certain amount of water that's applied over a given protected area. With pipe schedule, you size the pipe based on the occupancy hazard. You never took into account what the water supply was. However, with density now, you had to look at the occupancy and the water supply and match the two. So when it came to protection in the 1960s, we had some testing that was done to create a document known as NFPA 231C. And that consisted of about 25 tests that were used for protection of class 1 through 4 commodities. When we look at what was in the actual testing, it'd be interesting to see how many of you think that the percentage of tests with demand areas ended up greater than 280 square meters, which is our 3,000 square foot area. So that's 280 square meters is a relatively large size. Well, it turns out that there was 72% of the test results were actually had demand areas larger than that. And when you looked at the actual average size of the demand areas that we had from all the testing, it ended up being 490 square feet. So when you look at those results, the sprinkler at the time, the K80, was all that was really available. And we found that it was good for protecting office buildings and manufacturing, but it wasn't so great for protecting storage. So in the 1970s, we set on trying to find sprinklers that could protect storage. And the first one that came out was what we call the large drop sprinkler, known today as the K60. And it also ended up being known as a control mode specific application sprinkler. It gave you a new type of listing. In addition, instead of just the density over demand area type of design, there was a new type of format for the design. It took into account a number of sprinklers at a minimum pressure. So when we get to the 1970s, now we have sprinklers that are designed for density over demand area, and now we also have sprinklers that are use a design that's based on the number of sprinklers at a given pressure, two different types of formats. Also taking place in the 1970s, work was being done on sprinklers that could be installed in residential areas. And the idea was to have a sprinkler go on as quickly as possible to allow somebody to get out of the area without being affected by the fire or smoke. But in order to make that happen, we had to find thermal elements on the sprinklers that would react very quickly while the fire was small. And the research led to what we know today as a quick response thermal element. So when you look to the 1980s, when you look at what we had for large drop sprinklers and quick response sprinklers, the idea was maybe we can put the two of them together to end up with performance known as suppression. In the past we had control of fires. Now we're looking at how to suppress a fire. And we're going to do that with what's called the actual delivered density concept. And what do I mean by that? And you see a graph here behind me. And on the x-axis, we're going to use time as our variable. And what that is time when the fire first starts. So at 0 time, you've just lit the fire. Along the y-axis, we're going to show you amount of water. And that's the amount of water that's coming out of the first operating sprinkler. So when we look at our first curve, what that is it's called RDD, or another term for required delivered density. How much water do I need on the fire to suppress it? Now if you think about it, if I can get my sprinkler to operate while the fire is small, I won't need that much water. But if my sprinkler takes a long time before it can open up, you can see the amount of water I need is going to get larger because the fire is getting bigger. Our second curve here is actual delivered density, or ADD for short. And what that is how much water is actually getting to the fire area, the products that are burning. So again, if I look at the curve, it shows you I'll get a lot of water to that fire if I get the sprinkler to go off early in the fire stage. But if my sprinkler takes longer and longer to operate, I'm going to get less water down, the fire is going to be bigger. So our only opportunity to really get suppression is if I get that sprinkler to operate while the required delivered density is less than the actual delivered density. And it's a great concept, but at the time, the sprinklers that we had on the market really couldn't do that for us. And if my videos are working correctly here, you'll be able to see this type of sprinkler above you operating in the discharge pattern. And it doesn't appear that's going to be the case. Are we running this off the thumb drive? Okay, because there was a slide in there that wasn't on the thumb drive. So, what this led to was they get it here operating hopefully. You can tell by looking at the FM global symbol if it's kind of doing something. Yeah, I'm usually really good at that. I've got 6 videos, so hopefully we can get this corrected. it's a beautiful discharge pattern, but what's happening though is that all the water is going off to the side. There is no water that's taking place underneath. So if the fire starts off to the side, we're great, but if it starts under that sprinkler, there's no way to suppress the fire. So what we had to do was go ahead and go back to manufacturers and have them work on a new type of sprinkler concept that would allow water to be discharged below the sprinkler as well as in the umbrella pattern as well. So after this is done here, we'll go ahead and move to the next video, which will show you this one right here, which will show you what ended up being the very first ESFR sprinkler. Now, if you look at this, you can definitely see there's water going off to the side, but then now there's also a major water discharge that's taking place directly under the sprinkler. So now, no matter where the fire starts, we can get water onto that fire. In fact, with these types of sprinklers, I almost want the fire to start under that sprinkler because that's where a good amount of water is going. So from 1990 through 2014, we run a whole bunch of research tests. And what I'll do is I'll share some of the results with you just to see how it affected our sprinkler designs. The first one is density. So when I look at density, what happens with density, if I go install a sprinkler system using density, the flow and pressure out of the most remote sprinkler is dependent on the spacing that's used for the sprinkler. And so what happens is I can change that pressure. For example, let me give you a fire test we ran, where we used cartoned unexpanded plastics, stored 6 meters high under a 9 meter high ceiling. We used palletized storage, we used a K160 type of sprinkler, and we used a density of 24 millimeters per minute, pretty very strong density. Now, in the first test, we installed the sprinklers on 3 meter by 3 meter spacing, and based on, to give you a 24 millimeter per minute density, the pressure had to be 1.9 bar. In the second test, though, we changed the spacing. We reduced it. We went down to 3 meters by 1.5 meters and staggered the sprinklers. So all you needed was a 0.5 bar pressure to meet that density. Now, in the first test, what we saw is that we opened up a total of 18 sprinklers for a demand area of 165 square meters. Now in test 2, again, we changed the pressure, we reduced the spacing to half of what it used to be. So you would think if density is constant throughout, you would end up with about 36 sprinklers operating during this test. Well, that is not the result we got. We got a much, much larger demand area, even though it was the same density. So it sort of told us that pressure, if you change the pressure compared to what we had during the original test at the maximum spacing, it could be affected if you change that spacing. Also what we have on the market today is we have control mode density area sprinklers, which are designed for density over demand area. We also have control mode specific application sprinklers, which use some minimum number of sprinklers at a minimum pressure. Now they're different in category. So we have CMDA and CMSA, and they're also approved differently. But the question is, are they really different? So we ran a test way back about 7 years ago, where we ran 8 tests for a CMDA sprinkler, and we ran 8 tests for a CMSA sprinkler, so we could compare apples to apples. And we ran those tests. We used K160 upright, nominally rated for 70 degrees C sprinklers. And when we were all set and done with our tests, our conclusions were that both sprinklers are really the same as long as our key attributes of the sprinkler, which are K factor, orientation, nominal temperature rating, response time index, and sprinkler spacing are all the same as well. So let's take a look at sprinkler attributes. Okay, testing in the mid-2000s sort of told us that our designs really should be on the attributes of the sprinkler. And what those are just what we covered. So let's take a look at some videos and some fire tests that we ran and see how the attributes can affect the results of the test. What I'm going to keep constant during these 2 tests, I'm going to have a storage height of 6 meters, I'm going to have a ceiling height of 9 meters, and I'm going to use double row racks. Now in the first test you'll see, what I'm going to do is I'm going to use a K160 upright sprinkler rated for 70 degrees C. It's going to be standard response. The spacing will be on 3 by 3 meter spacing. The aisle width will be 2.4 meters. And the density I'm going to use is 32 millimeters per minute, so a very strong density. So let's hopefully see if the video works in this particular case. Okay, it's actually working. Great. So what we're going to do is, you can see we've got our carton. This is carton unexpanded plastic. And as the fire takes place, you can see a clock in the upper right-hand corner. Now what I'd like you to focus in on is at what time the first sprinkler opens up during this test. Okay, there we go. So it's about 1 minute and 19 seconds into the fire, we get our first sprinkler opening. And you can see that with a 32 millimeter per minute density, that's a lot of water. It's driving that fire down back into the rack. However, what happens during this test is that the water that's being discharged really can't get that fire all the way down. And in any second, you can start to see it now coming back. And so the flames are getting a little bit larger. Now, what happens with control, though, is we'll get the surrounding sprinklers to go off, and they'll hopefully pre-wet the surrounding combustibles so the fire doesn't spread horizontally on us. We don't want it to spread down the length of the rack, nor do we want it to jump across the aisle and burn into the adjacent racks, or that fire can really take off on us. Now, as you watch this video, I don't know if you can really see it, but there's smoke accumulating at the ceiling. And luckily that's being taken away and cleaned up and sent to the atmosphere, so it's nice clean air. But what this does for us, it allows us to actually continue to watch this video. Otherwise, it would be blocking our view. At the same time, you can tell when other sprinklers at ceiling level have gone off, because when they operate, the water coming out of the sprinkler will go down through that smoke layer and drag the smoke with it. So as we watch this video, you can see that it's a good thing that we have a 2.4 meter wide aisle. Otherwise, that fire probably would have jumped. And here we are, we're coming up on 3 minutes into the test, and you can see that I haven't opened up any other sprinklers. Now, these sprinklers are rated for 70 degrees C, a relatively low temperature, so I wonder why with that heat that you see there being given off during this fire, why no other sprinklers are going off? So this is starting to not look so good, is it? But in a minute or two, in fact, what you might see is there was a sprinkler that went off back behind the fire, but that sprinkler was 6 meters away horizontally. It wasn't the nearest sprinkler going off, which was only 3 meters away. And if you look now, you can actually start to see a fire starting to develop on the adjacent storage rack. And there it goes. Now we've got the fire that's jumped the aisle and starting to get involved in the adjacent rack. But now we're going to start to see some sprinklers actually going off. We're going to start to see the smoke come down and block our view. Now, as we watch this, this looks like a complete disaster of a fire. Looks like the sprinklers didn't work at all. But in reality, when everything was all said and done, we opened up 25 sprinklers, and they were able to control the fire. Now, this might be strange to you, but that's what control type performance looks like. It's a lot of fire, a lot of water, a lot of smoke. But the sprinklers are able to keep that fire from spreading horizontally and keep the temperatures at ceiling level from getting too high to collapse steel. So in this particular case, we opened up 25 sprinklers. Now for our next test, we're going to make some changes. So instead of a K160, we're going to change the K factor. We're going to go to a K360, a much larger sprinkler. We're going to go to a quick response instead of a standard response sprinkler. The spacing is going to change. We're going to go from 3 meter by 3 meter to 4.2 meter by 4.2 meter. So this is an extended coverage sprinkler. And while we do this test, guess what we're going to do? We're going to make the aisles narrower. We're going to go from 2.4 meters down to 1.2, and we're going to reduce the density. So instead of 32 millimeters per minute, we're actually going to drop it down to 24 millimeters per minute. So let's see how we do with this particular test. Now, in that first test that we saw, we had the first sprinkler operated at 1 minute and 19 seconds. Now, This sprinkler is rated for the same temperature. These sprinklers that we're looking at are both rated for 70 degrees C. So here we go. We've seen the fire has been lit. It's the exact same commodity, same volume, span of plastic, same storage height of 6 meters, and a ceiling height of 9 meters. So as the fire comes up, you'll start to see it get above the top of storage here. And here it comes up. And here at 39 seconds, our first sprinkler goes up. So the first test had 1 minute and 19 seconds. This one's actually at 39 seconds. And what you're going to see the water do from this sprinkler is it's going to take that fire and it's going to drive it back down towards the base of the rack. The water coming out of that sprinkler is actually getting onto the surfaces that are burning and suppressing this fire. So at this point, the only amount of fire we have left is a little bit of fire in that bottom tier. So when the fire surfaces show up, all they see is a little bit of fire in the bottom, and one hose stream can hopefully put it out. In fact, we've just reached the time that the first sprinkler operator rated in their first test. So you can certainly see a major change based on the attributes of the sprinkler. So here's a case where we only open up one, and you can see we've used less density to do it. So the attributes have a major impact on the performance of the sprinkler, the fire protector. Assumed performance, what do I mean by that? Well, when you look at today's listings, we have control mode density area sprinklers, we have control mode specific application, and we have suppression mode sprinklers. Now, the listings basically tell you what we assume they will do. All those control mode sprinklers will control the fire. That's what we saw in that first video. And the suppression mode sprinklers will suppress the fire. That's what we saw in that second video. So let's take a look at a couple of videos here and see what sprinkler do you think we have installed at ceiling level. Now, in this first test, what you're going to see is we're going to run a test with carton unexpanded plastic. And our storage will be 6 meters high under a 9 meter high ceiling. We'll have our storage in double row racks with a 1.2 meter wide aisle. We're going to use a density at ceiling level of 24 millimeters per minute, and we're going to start the fire directly under a sprinkler. So let's see how this works out. Okay. Again, the clock has been started, so you can see that the fire has been lit. Fast forward here to about 1 minute and 5 seconds. Up comes our fire in the rack. And off goes our first sprinkler. And what this sprinkler is doing is, again, it's taking that fire, water is being applied to the vertical surfaces that are burning and basically extinguishing those surfaces. And all we have left is some horizontal surfaces where the water can't get, and that's what's still burning. But there's not much fire here left over based on the performance of this sprinkler. And in this test, this is the only sprinkler that went off. So in this case, we had one sprinkler that operated during this test and suppressed the fire. So what sprinkler did we install at ceiling level? One would think it was a suppression mode sprinkler, but it wasn't. It was a control mode sprinkler. In fact, it was a K360 extended coverage quick response sprinkler. Now, the funny thing about this is that this sprinkler, the requirements for this sprinkler, when you look in the code, say, you know what, you need a higher density than what you used, and you need in-rack sprinklers. Well, obviously that's not the case for this sprinkler. Let's take a look at another test that was run. In this case, it's lightweight wallpaper up to 7.5 meters high under a 12 meter high ceiling. We're going to have the storage protected by a 48 millimeter per minute density. And we're going to start that fire again under one sprinkler. Now, whatever you do, when you watch this video, don't blink. Okay, here comes our fire. Here it comes. Now, don't blink. We're 43 seconds into this fire, and we've opened up 16 sprinklers at ceiling level. And you can see there's a lot of fire going everywhere, there's a lot of smoke, a lot of water from the sprinklers. In fact, the smoke's going to block our view, but we're going to fast forward so you can see the flames again. Here we are, 3 minutes and 17 seconds. And you can see there's quite a little bit of fire still taking place. But we let this fire run for 30 minutes. And during that 30-minute time frame, the fire stopped going anywhere. It was contained to this one spot. So the water came on, pre-wetted the surrounding combustibles, and stopped the horizontal fire spread. So it controlled the fire. Had to do it with 16 sprinklers though. So what type of sprinkler do you think we installed at ceiling level? Well, if you're on to me by now, that was an ESFR sprinkler, suppression mode. It was a K200 quick response pen. So there was a suppression mode sprinkler that's supposed to suppress fires, but it didn't control it. So what are we going to be doing beyond 2014? What we at FM Global are looking at are a couple things that will change our protection criteria for storage protection. One of the things that we're going to focus in on is in-rack sprinklers. Okay? Today's guidelines say that if I have in-rack sprinklers installed, I can't store any storage above 3 meters above that top level of in-rack. So we want to see, can we change that? In addition, we're going to look at the key attributes of in-rack sprinklers and see if we can increase the vertical installation spots of where they need to be installed. Right now, sprinklers in racks are typically needed every 3 meters vertically. We're looking at if we can come up with a in-rack layout that will allow us to avoid the need to hydraulically balance the ceiling sprinkler system and the in-rack sprinkler together. And if we can accomplish that, the idea is we can do it in such a way that you don't have to account for the ceiling and the in-rack system to be flowing concurrently. That'll help us in terms of the size of water supply. So when we look at our goal, whenever you need a warehouse that actually needs in-rack sprinklers, let's find a way to come up and minimize the amount of in-rack sprinklers we have to install. First thing we'll do is look at how high above the in-racks we can protect with our ceiling sprinklers, and then look at ways to maximize how much storage we can have below the in-rack sprinklers, and that'll help us minimize the amount of in-racks that are present. And ideally, if we make this work, we'll have what we consider a fictitious floor that will be above the in-rack sprinklers. It won't be there, but it'll be a design that's as if one was there, so you can look at the in-rack separately compared to what the ceiling system requires. So how are we going to achieve this goal? There's lots of things we have to do. We have to, first of all, understand how fire grows within a rack storage, whether it's class 1 through 4 commodities or plastics. We have to understand the application or the characteristics of our sprinklers that are installed as in-racks. We need to understand how water gets down through the racks and gets to the fire. And then, once we do that, we can learn how to model this on a computer standpoint. We'll investigate partial potential solutions via small and intermediate scale. Once we have that, we'll finally put it to the test and run some full-scale fire tests to see if it actually works. So the first thing we're going to do is we're going to look at our fire growth and suppression. So what we do is we start off with a free burn. So when we look at our heat release rate versus time, we'll see the curve goes up. You eventually get to a certain rate of free burn, and then it comes down. The next step we'll do is we'll provide some water application. So we'll run a test, we'll supply some water to the burning commodity. The idea is to find out how that water affects the results of that test. So we'll apply water. If we apply too much water, we'll suppress that fire. Ideally, what we're looking for is an amount of water that provides a steady state control. So that becomes the minimum amount of water needed to provide control of that fire. What we learn from that is our fire growth dynamics as well as what we need from a suppression efficiency of the sprinklers being delivered. So once we know the fire aspects, we look at the sprinklers themselves to find out how they're delivering water. So we look at water being applied close to the sprinkler as well as far away. And from there we can get an idea of where this water is going. The next thing we need to know is how the water interacts with the product that we're trying to protect. And when the water hits the product, how will it slide down? If it's burning, how will it evaporate? So we look at cases where we've done testing with no water flow condition. So we can see water flowing down the boxes that need to be protected. And then we apply heat. We see how the water interacts with the burning commodity, and from there, we can then learn how to do it from the standpoint of a model. Then, what we do is we put it all together. We look and see how the fire growth modeling works with the water, and we run some intermediate scale tests to find out if our protection modeling ends up working. And what that does, it gives us an idea of what to run for full scale. So, when we put it all together, the idea is to find out how high we can go where our in-rack sprinklers happen to be. And we've done some full-scale fire testing to validate it. And what we found so far is, depending on the commodity hazard, it can be anywhere from 9 meters up to a height of 12 meters for some of our commodities. So in conclusion, what have we found? We've looked and we've determined what we have for vertical increments that we can use in-rack sprinklers at. We've created that, it's not working very well, we've created that fictitious floor, so we run tests where we've actually opened up in-racks only and haven't opened up any sprinklers above them. So we've created a condition where only the in-racks will open up. We've now been able to create a situation where we can increase that 3 meter limitation on the storage above the in-racks. We've also done research to find out where the sprinklers have to be in relationship to the flue spaces, as well as in their proximity to the rug crack uprights. And we've also looked at clearances of where the in-rack sprinklers have to be when it comes to distance above the top of storage. And we've looked at a lot of other things as well. And the whole idea is that when everything's all said and done, we'll end up putting it in the FM Global data sheet for you to see in the future. And that's probably going to be around 2016. So with that, I'd like to open it up to the floor and see if there might be any questions. No questions? All right, well, I guess I'm the, oh, okay, we do have some questions.
Boa tarde, eu sou Fábio Maza, da Axa Matrix Consultoria de Riscos. Eu queria perguntar, hoje no datasheet da FM, então eu sou Fábio Maza, da Axa Matrix Consultoria de Risco. Hoje no datasheet da FM, nós temos situações de in-racks, em vários casos para plástico não expandido ou expandido, isso não em caixas de papelão, né? Em que você tem in-racks tanto dentro do flue space como face sprinklers. Eu queria saber se no próximo datasheet da FM o conceito de in-racks, tanto flue como face, em todos os espaçamentos, se ele vai continuar, se existirão mais alternativas com in-racks somente uma linha no flue space, ou como que vai ficar a distribuição dentro do arranjo de estocagem.
Thank you very much. When it comes to the current in-rack arrangements that we have at 8-9, there are some, when you get above 7.5 meter high storage, there are cases where you can have in-rack sprinklers in the longitudinal flue space only, nothing out at the face. But that's limited right now to cartoned plastics. In fact, we ran some tests recently with exposed plastics, trying that same protection scheme, and it didn't work. So we've got, what you will see going forward in 8-9 is anytime you have the exposed plastics, whether it's expanded or non-expanded, we'll still be looking for in-rack sprinklers at the face when the storage is above 7.5 meters. If you don't see any ceiling-only options in the protection table. So once you need in-racks for those plastics, you will need longitudinal in-rack sprinklers and face sprinklers as well. Now, we ran tests that you saw today, where you could create a fictitious floor. It did include sprinklers in the longitudinal and also at the face. But using the larger K-factor sprinklers with a good amount of water, we were able to avoid the fire from getting above the in-racks, allowing us to then create a condition where you could do an in-rack design, you could do a ceiling design based on what's left above, but you didn't have to balance them together or need them both at the same time. So currently, 8 and 9 in-rack options will still be there, and then what we discovered today with our testing will supplement what's currently in there. I don't see any more questions, so I know I'm between you and your coffee break, so thank you very much for having me in today. Thank you.